Okay, we've covered most of the first half of the extended first law now, and we're ready to begin looking at the second half, the part that has to do with heat and work. But before we do that, there's one more topic that we need to look at, and that's this thing called extensive and intensive variables. An extensive variable is one that represents a quantity of stuff, either energy or volume or mole numbers. An intensive property is one that represents a force or a per mole quantity or some kind of ratio quantity. We'll talk a little bit more about that. So temperature and pressure and chemical potential are all intensive properties. The difference between extensive and intensive comes up several different places. It's not the most important thing, but it does come up, and so we should talk a little bit about it in several different relationships, as we'll see as we go through. So the real definition, I've given the sort of heuristic definition here, but the real definition is this. If I double the system in every way, does quantity X double? If it does, then it's extensive. Does it stay the same? If it does, then it's intensive. And so, for example, let's look at some quantities. I have 1 mole of water. I have energy, volume, mole numbers. When I double the system, I've got 2 moles of water over here. I've got twice as much energy, right? I've got twice as much volume. So all those quantities double. Those are all extensive. On the other hand, there's temperature, pressure, and chemical potential. The temperature doesn't double. It's the same everywhere, even when I double the system. And the pressure doesn't double either. And the chemical potential is less familiar to people, but that also doesn't double. So those are intensive. If I take the ratio of 2 extensive quantities, so if I take U per mole, for example, or molar volume, moles per unit volume, or energy per unit volume, energy density is what that amounts to, then those are all intensive quantities, right? Because they both double. They double on the top and they double on the bottom if you double the system in all 3 cases here, and that means that the overall ratio doesn't change at all. And that's true for the molar enthalpy, for example, when we talk about that, the molar Gibbs free energy and so on. It's also true for a derivative quantity like this one. So if I take the derivative of the energy with respect to the volume, we haven't talked about these kinds of derivative quantities yet, but we will. That turns out to be equal to minus the pressure. Well, that's obviously an intensive property too, and you can see it in the derivative, right? If I double U and I double V, then U over V, or du dV, doesn't change, and so it's also intensive. All right, that's enough said about that for now. We'll talk about it more when the topic comes up later. Now we're ready to talk about the second half of the extended first law, and it reads, the energy of an isolated system is conserved. Energy is conserved. For open systems, which are not isolated, right? So an isolated system means no interaction with the surroundings. Of course, the system energy can't change in that case. But if the system is open, then the energy can change, but it can only change in 2 ways, either by heat or by work. So the change in the energy of the system is equal to a heat change plus a work change, or if it's a small energy change, then a heat change, a small heat change, and a small work change. The first part of the extended first law was talking about states and variables, very important and very, very basic. But now this part, we're starting to talk more about the rules for how the system itself behaves. We're talking at least about, in this case, how energy is transferred in and out of the system, or in the case of an isolated system, what happened, the fact that the energy is conserved. All right. The fact that energy is conserved means that the total energy inside the system can't change, but it can still move around, right? If I've got 2 little parts, subdivisions within my system, then energy can move around inside the box. It just can't move. The total energy can't change, which means that whatever energy is lost by one part of the box is gained by another part of the box, and vice versa. On the other hand, if the system is not isolated, if it's open to the environment, if the environment is doing something to it, is interacting with it, the energy can change, but there's only two types of energy transfers that are possible. So heat and work are not special kinds of energies in their own right. It's all just energy. There's only one kind of energy. Heat and work are methods by which energy is transferred from the system to the surroundings or vice versa. What are them? Well, we're going to talk extensively about both of them, so let me leave that aside for the moment. And here's what I just said. Heat and work are methods of transfer, and they're the only methods of transfer. If energy changed, then you know that it has to be some combination of heat and work, either pure heat transfer or pure work transfer, or some combination of the two. All right. The first of them, and the most obvious of the two, the one that's common even outside of thermodynamics, is work. It's a physical quantity. It's defined in physics. And here's the physics definition. A small quantity of work is equal to some kind of force, and in thermodynamics we have to talk about what that force will be, times some displacement dx, the most common case. And so that's for a small work. If you've got a finite amount of work, then you just add up all the small works, and so there's an integral involved, but it's not a different idea. Force times distance is work. If I have a system like this, a cylinder with a piston in it, and there's gas inside the cylinder, and I have a force that's external, so that EXT means this is the force from outside, then there must be a compensating force on the inside that we'll call F internal, F int. And those two forces have to be balanced at all points. That's just physics. The external force is just what it is, but the internal force, it's useful anyway to think of it as having a bunch of different pieces or parts. There's a system-generated thermodynamic force, like the pressure creates a force on the cylinder. Pressure times area is a force, right? But there may also be forces due to friction as this piston moves up and down. It may rub against the walls. There are also viscous frictions inside due to the gas flows themselves, or maybe it's not gas in there, maybe it's a liquid or something. Whatever's going on in there, it can also cause frictions. And then the piston itself may have some mass, in which case there are inertial forces. So all these forces aren't necessarily simple things, but at all points the internal force and the external force have to balance each other. And that's shown kind of a little bit better here. There's all kinds of things going on. The external force is pushing down on the cylinder, let's say, on the piston, let's say. It has a certain mass. As the piston starts to accelerate due to the external force, there's a back force, the force of inertia. Every kind of mass resists being accelerated a little bit. And there may also be friction against the walls. But also there may be swirling gases or swirling fluids or liquids or anything inside. And some of that at least gives rise to sort of an intrinsic viscous friction that also resists the movement of the piston. And of course, the pressure inside is also going to result in a system force that will push back against the external force. So yeah, the forces have to balance at all times. But if we want to calculate how much the system energy is changing, either a finite change or a small change, then the only thing that matters is the external force. The work done by the external force is the part that changes the system energy. If the external force does work on the system, then the system gains energy. If the external force has work done on it by the system, then the system loses energy. But the internal force and all these complicated things don't change the system energy because they just, for example, looking at some frictional forces down here deep inside the system, Yeah, there's all kinds of frictions and forces and works that are being done in here, but they don't transfer any energy out or into the system. They just transfer energy around inside the system. So this total system energy doesn't change because of them. So that means that the work that we're concerned with is just one term or one contribution, and that's the part that's done by the external force. That's the part that causes a net change in the overall system energy. And because the external force has to always be balanced by the internal force, whatever complicated things make up that internal force, that means that the work is equal to both F external times the displacement and minus F internal times the displacement. All right, that's the general case. I put a little green box about this to indicate that this is a basic formula. We probably won't use it, though, after this moment anyway, because all of the work, or well, not quite all the work, but much of the work that we're going to talk about this semester will be pressure volume work, and so let's look at that particular special case. In that case, we've got pressure, an external pressure on the outside. We may also have a pressure on the inside, but that's not going to contribute to the work because it's only the external force that we care about, right? Just that's the only thing that's existing and that contributes to this formula. And that external force is minus the area of the piston times the external pressure, and therefore the external work, a small amount of external work, is minus the external pressure times dV, right? The area here times the small displacement turns into a volume element, dV, when they get multiplied together. So our new formula, our new important formula with another green box, is dW is minus P external times dV. This is the most important thing to remember from this little last chunk of the section. Now let's take some special cases. Special cases are always important. Let's consider the case where the external pressure doesn't change. The piston moves, but the external and the volume changes, but the external pressure doesn't change. It's constant for some reason. For example, because there's a pressure bath outside. That's the most common case why the external pressure doesn't change. It's all one atmosphere, and the piston moves and does work, but external pressure doesn't change. In that case, doing the integral in our definition here, we get that work is equal to minus the external pressure, the constant external pressure, times whatever the volume change is. A nice, easy formula. Let's do an example. I have a system with the external pressure set at 1 atmosphere. That's never going to change. The volume goes from 2 liters to 1 liter, so I compress by a liter. The external pressure is 1 atmosphere. The volume change is minus 1 liter, right? It lost volume, so this volume change can be positive or negative. In this case, it's negative. So the work is minus 1 atmosphere times minus 1 liter, which is a total of a plus 1 liter atmosphere. Those are weird units. This work has to have units of energy. A liter atmosphere is in fact an energy unit. There's nothing wrong with it, but it is very non-standard. So let's convert it. 1 liter atmosphere is equal to 1 liter atmosphere times 1 joule per liter atmosphere, but I put these extra things under here, K and moles, because that means I can use the known values of the gas constant to get my conversion factor. I use the gas, this is R in joules per K per mole, this is R in liter atmospheres per mole per K per mole, and you can see that they provide basically a units conversion factor between liter atmospheres and joules. That's the trick I'm using. The value you get is 101.3 joules. So 1 liter atmosphere is about 100 joules. And we won't use calories in this class, but they are out there. They are commonly used. You can use the same trick. Here's the gas constant in joules. Here's the gas constant in calories. And so 1 calorie is about 2 joules. Joule is the smallest unit. Calories in between, and liter atmosphere is by far the biggest unit. Notice also the sign here. We got a positive work. In this case, we did work, right? The external pressure compressed the system. That means the system energy at the end was higher. than it was at the beginning. We compressed the gas, that's stored potential energy now. So the system energy went up. And we got a plus sign. That means that the way we've set things up, it's possible to set things up differently, but the way we've set things up, this W here is a change in the system energy itself. The system energy goes up when W goes up. W goes up when the system energy goes up. And so in this case, when we're compressing, we got a positive value. The negative sign gets canceled by a negative sign on the delta V, and so we get a positive value. On the other hand, if we were expanding, delta V would be a positive quantity, and the minus sign would make work negative in that case. That means the system lost energy in the case, or in that case. Or in other words, the way to put it is to say that the system did work on the surroundings, whereas in the first case, the surroundings did work on the system. All right, now we come to a thing which is just about the subtlest thing there is in all of thermodynamics, maybe one of the subtlest things in all of physics and physical chemistry, and that's the distinction between a reversible process and an irreversible process. I will confess to everyone that I did not understand this business at all for a very long time myself. So I will take a little bit of time here. The distinction between reversible and irreversible is important in certain settings. It isn't terribly important in most of chemistry because things are almost always reversible in chemistry. But I will take some time to get this straight here for those who are going to go on, and we'll see these concepts again. I think it's important that people get at least a good first exposure. All right. Reversible work is the following. It's a process that was done slowly, which means there's no friction, which means things were under control, no popping, no explosions, no fire. Things were happening slowly, so there's no friction. Especially important is that the system, therefore, is always, I say, at equilibrium here. But the system couldn't move at all if we were actually at equilibrium. But the idea of a reversible process is one that happens slowly enough so that we're so close to equilibrium that it makes no difference. And so I say at equilibrium, but it just means really, really close to equilibrium. As close to equilibrium as you like. If you do some process and you start getting funny results and you think it's because it's not really reversible, you can always just slow down and get closer to equilibrium. And then the funny results will presumably go away. In the present context, it means that the internal pressure and the external pressure are always in balance. If you're always at equilibrium, then the external pressure and the internal pressure have to be balanced, right? If they're unbalanced, things will move, and they won't move slowly necessarily either. So you'll get friction, and you'll get out of equilibrium. So the internal and external pressure are balanced for a reversible process. That means we can just talk about P. We don't have to talk about whether it's internal or external anymore since they're the same. And that means that the work for a reversible process is just minus PdV. No distinction again. I mean, the correct true formula that always works is P external here, and that's also true, of course, for a reversible process. But if it's a reversible process, then you can replace the P external by just whatever the pressure happens to be. What this thing really means, and now we're starting to get a little closer to why we're making this reversible, irreversible distinction at all, is that if I, for example, compress a system and calculate how much work I do as I compress, and then I decompress again reversibly, I'll follow the same path back. The same series or sequence of pressures and volumes will occur on the way back, except in reverse. And that means that the work that I do on the way back will just be the negative of the work that I did on the way forward. And there'll be no net work change if I return back to my original state. So if I start at 1, go to 2, and then start at 2 and go back to 1 by reversible processes both ways, I'll have done no net work overall. There'll be no energy change overall. That's a reversible process. That's what it means to say that the process is reversible. What about irreversible? Well, now you do have friction. Now you're doing some of the work you're doing, some of the external force that you're exerting isn't working against the thermodynamic forces that the system generates. It's working against friction against the walls or swirling viscous friction inside, that kind of stuff. You're doing work against something that has to do with how fast you're compressing the system and not with the properties of the thermodynamic properties of the system itself. And so friction is a kind of a deal breaker for a lot of thermodynamic calculations. And an irreversible process by definition has some friction, so you've got to watch out for that. It also means the system will not be at equilibrium. Anytime you're getting friction, you're not at equilibrium, at least not all the time, right? A little bit of friction in the middle of a process makes the whole process irreversible to some extent, right? How irreversible something is depends on how fast and how much friction there is, and a little bit of friction is probably negligible, but at least there's some friction. And it is therefore somewhat irreversible. That means the internal pressure and the external pressure aren't necessarily the same, at least not all the time. And now you got to use the full formula, and the proper pressure, since they're different now, is to put the external pressure in there. And now looking at what happens if I do some process and I follow the pressure and volume changes as I do, I'll get a certain sequence of pressures and volumes, but they'll be different than if I were doing the process reversibly, because we're not at equilibrium all the time, and exactly which pressure I get at every point as I'm compressing will depend on how much friction and swirling and all that stuff that's going on. And then if I try to reverse it, since I can't really reverse all that swirling stuff, I'll get a different sequence of pressures and volumes as I'm going the other way. And now, a useful thing to point out. If the work is equal to the integral of the force, or the pressure, times the volume change, then on a pressure volume diagram like this, right, pressure and volume, the work is just the area under the curve. So if I do something like this, that's probably for a reversible process, or it looks like one, then the work is just this area underneath that curve. Well, in this case up here, that means that the work I do in the forward direction is this area under here, under the first curve. But the work I do when I'm going backwards is the green hatches here, the area under that upper curve. And that means that the net work that I do going all the way around, if I go all the way forward and then all the way back, isn't zero anymore. The forward work and the reverse work are not opposites to each other. And that's something called hysteresis. That means going back and going forward, you don't get the same result. And that's what really we mean by irreversible. It means that the system energy changed, right? The net change in the system energy is the change in the work now, is going to be the area inside this loop, this hysteresis loop. And that's not zero anymore. Up here it was zero, right? No loop here, therefore zero. A loop here, therefore not zero. That means we put work into the system, we put energy into the system, even though we got back to the same state. We started from a state, we returned to the same dang state, but we put energy in anyway. And at least as far as, let me not belabor that point. And so we didn't really reverse the system. We changed the system energy. This energy that got put in because of friction, right? We did some work against friction that ended up inside the system, and it's still there when we went back. So we basically did a bunch of sliding and scraping that added the energy to the system, even though we returned back to the original pressure and volume. All right, let's do an example. So here's an irreversible process. I start with the system at a certain pressure and volume here at state 1. I do a step where, this step A, where I lower the pressure, but I don't change the volume. Volume's constant that whole time. Can I even do that? Well, there are ways to do it, but it doesn't sound very reversible, right? You're not keeping the pressure on the inside and the outside the same when you do something like that. And then the next step, the next leg of the process, I do the reverse. I hold the pressure constant. The external pressure now, notice, not the internal pressure, because we don't even know what the internal pressure is. I hold that external pressure constant, and I change the volume. I allow the volume to change. That's path 1. Here's another path, path C and D. So AB is path 1, CD is path 2. I do just the opposite order, right? change the volume without changing the pressure, and then I change the pressure without changing the volume. Let's see what we get for work in those two cases. These are cases where the pressure is always constant whenever we're doing anything, here, whenever we're doing any volume change. So we can use our constant pressure expression up here. Where is it here? That work is equal to minus P external delta V. Notice this is true whether it's a reversible or irreversible process. Later we'll talk a lot about reversible processes, and then we have to be a little careful. But this formula is good, always good, whether it's reversible or irreversible. So down here again, let's do the calculation. So we're going to go for the AB path here, path AB. Start, let's say, with a pressure, an external pressure of 10 atmospheres and a volume of 1 atmosphere. That's our state 1 up at the top. Then we change, that's path A here, step A, to a pressure of 1 atmosphere and still a volume of 1 liter. Haven't changed the volume, just changed the external pressure. No work in that case, right? No delta V. Delta V is 0, so work is also 0. All we did was lower the pressure on the outside. And I have a little pin drawn here to indicate that I'm holding things in place, right? Presumably the pressure inside here is now greater than the external pressure, but I'm holding it in place with the pin. Now I take the pin out. Once I take the pin out and there's a force imbalance, there's a pressure imbalance like that, that piston's going to move, right? And if it's a light piston, it might move pretty fast. So this looks like an irreversible situation, just sort of intuitively. And I'm doing it against a constant pressure of 1 atmosphere. It changes from 1 liter, the volume does, to 10 liters. So now there is a work, and it's equal to the pressure times the volume change. That's 1 atmosphere times 9 liters, and that's 9 liter atmospheres, or 912 joules, minus 912 joules. This is a case where the system is doing work on the surroundings, and so the system's losing energy, and that's reflected by that minus sign. Again, okay, so the overall net work for the whole 2 steps combined is minus 912 joules. And that's the area under the little curve, right, for this A-B step process. Now the other path, in that case, I start with the same state I started, state 1. By the way, this is state 2 now here at the end here. Here's state 2 up here in our original diagram. I start with the same state 1, 10 atmospheres and 1 liter. I keep the pressure constant, right? That's this leg of the overall path, keeping the pressure constant. But I change the volume. So in this case, somehow, even at this 10 atmosphere pressure, the volume inside, the pressure inside apparently is high enough to allow I mean, I haven't said what the pressure inside is, but apparently it's high enough to allow the piston to move anyway, and it goes from 1 liter to 10 liters. So it's the same volume change as before, but now under a higher pressure. And there's work for that because both the pressure is not 0 and the volume change is not 0. And it's 90 liter atmospheres, which is almost 9,120 joules, minus again. A much bigger, basically 10 times bigger pressure change this time than, or work change, sorry, this time than last time. Then for the next step, I just change the pressure on the outside without any volume change, so no work on that step. And the overall work is then minus 9,120. And the overall work for both paths together, so let's suppose I take the first path, and then I go back by the other paths, but going in reverse, right? Not now going this way on both steps. The work, the net work, is going to be the area inside that square, which is about 88,110 joules. Okay, so the complete cycle, I start at state 1, I return to state 1, the overall work is not equal to 0, the net work is 8,110, that has to be against friction or some similar dissipative process. And that means that the work can't be due to thermodynamic change, it must be due to friction. This must be an irreversible process. Anytime you see a loop like that, you know you've got an irreversible process. Here's an example of a reversible process. I'm going to say that this is a reversible process done under isothermal conditions. That is, I have a temperature bath out here and these walls are not insulating, so heat can flow in and out. I'm going to say it's either an expansion or compression. The piston moves either up and down, and I'm saying that there's an ideal gas inside, because now, since this is reversible, I'm going to make use of the fact that the internal pressure and the external pressure have to be the same, and saying it's an ideal gas then lets me know what the pressure on the inside, and therefore also on the outside, is, because I can use the ideal gas law, PV equals nRT, or P is equal to nRT over V. And that's going to be true at all points during the course of the process. Now let's use our work formula. dW is equal to minus PdV. The P is whichever in this case, so just P. Therefore, the total net change is the integral from the initial volume to the final volume of minus PdV. Plugging in the ideal gas law, that's minus nRT over V. Factoring out the constants, T is a constant in this case, right? Doesn't change in the integral. Minus nRT, the integral of dV over V, that's one of our standard integrals from the math review. It's a logarithmic integral, and we get that the overall work now for a reversible, reversible isothermal expansion or compression of an ideal gas is minus nRT log V2 over V1. That's an important formula. Actually, it's in the homework. So it's important for the homework. It's also important for a whole lot of things that we're going to do later. So, all right, at that point, we're ready to start talking about heat, and I'll save that for the next lecture.